An apparatus is used to investigate the photoelectric effect. A cesium cathode C is illuminated by a variable light source. A variable power supply is connected between C is cathode, and the collecting anode A. The photoelectric current is measured using an ammeter. All right, let's see. A current is observed on the ammeter when violet light, right? So this is short wavelength, right? Short wavelength, high energy, right? With the voltage held constant, the current becomes zero when violet light is replaced by red light. Well, red light is long wavelength, right? Small energy, right? Okay, explain this observation. Well, remember what the photon energy turns into the work function plus the kinetic energy max, right? Okay. And so possibly what's happening here, right, is that the violet light has enough energy to overcome the work function, but the red light doesn't have enough energy to overcome the work function. And so no electrons are emitted, right? Remember, the work function is the minimum amount of energy needed to eject an electron from the metal. Some of the energy from the photons could be lost to heat. Could also be that you're trying to eject electrons from metal, atoms that are further, electrons that are further into the metal than the surface. But this is the minimum amount of energy needed to eject an electron. It could be more than that, right? So anyway, I'll let you go at that, right? Okay, the graph shows the variation of photoelectric current with the potential difference, right? So this is, by the way, notice that this is negative. This is voltage slows the electron, okay? That's supposed to be slows. This is the voltage slows the electron. This is the voltage accelerates the electron, right? Because you've got the photoelectric surface here. And if we make this, this is our cathode, here's our anode, right? Okay. If we make this side positive, which is what they're talking about here, this is positive voltage, right? Then the electrons, any electron that's ejected, right, is going to accelerate across it. It definitely will make it across, right? And with enough voltage, right, we call this a saturation current. And the reason why the current goes up to a certain point but doesn't go any higher is that there's a one-to-one correspondence between photons and electrons. Okay, so the intensity of the light source is increased without changing the wavelength, right? So the photon energy doesn't change, right? But the intensity changes, right? Okay, so draw on the axes a graph to show the variation of the current with the voltage for the increased intensity. Well, we know that when we get out here, if increased intensity for the photon theory just means more photons, right? So therefore, we have a higher saturation current. Okay, so we know at the end here that this thing is just going to be a higher line, right? Because there we go, right? Okay. And then if it's the same wavelength, right? This is the cutoff voltage here, right? This is the stopping potential. So you're going to start here. You're going to do something like that, right? Whoop. Okay. And then in this range is just the notion that for very small accelerating potentials, it's still possible that the photons are trying to dig electrons out from deep in the metal, and so not all of them are emitted. But at some point, you know, if we have enough accelerating potential, the current just goes up to some maximum like that. Okay. The wavelength of violet light is 400 nanometers, determined in electron volts, the work function, right? Okay. Well, what we're going to have to do here is figure out that the stopping potential, right, is 1.15 volts, right? Right? Okay, and so we're just going to go, okay, photon energy equals work function plus the kinetic energy max, right? You're going to have to figure out the photon energy, so do your energy is hc over lambda, right? And turn that into electron volts, right? Okay, we know that our kinetic energy max is 1.15, right? Okay, so you can, you can figure that out, right? I get that the electron volts of this is somewhere between 3 and 4 electron volts, right? And then just set up your equation, right? You're going to have 3.1 equals 1.15 plus whatever that work function is, okay? And I got my work function was more than 1 electron volt, less than 2. All right. The voltage is now adjusted to positive 2.5 volts. Okay. So notice that we're stopping it. Normally when we do the photoelectric effect equation, we're trying to stop it. But now we're going to actually accelerate the electrons across, right? Okay. So calculate the maximum kinetic energies just before they reach the A, right? Okay. So now it's going to be the energy of those photons that you figured out here, right? Plus 2.5 volts, right? Yeah. And then, there you go, right? So figure out the figure out what that photon energy is, right? It'll be the photon energy plus the 2.5 volts rather than minus, right? Okay. I think that's it.